Right now, we are in the midst of a massive interstellar shift, and this is completely transforming the energetic characteristics of not only the Earth and of the Sun, but of the entire solar system. This is a process that's either currently unfolding at this moment in time or is about to happen. There's a little bit of uncertainty, but we do know that we are at the edge of our local cloud in the local interstellar medium. This is a zone of plasma that's kind of unique to our area. It is a fairly low density and a high temperature, and we're about to shift into a new cloud of plasma that is kind of unknown in its characteristics. We suspect that it's denser. We don't know though the temperature, and in general, this could be a massive shift for our solar system overall. Could be unfolding right now at this moment in time. If there's a transition zone between these clouds, we could be in the middle of that. And there is evidence from the geologic past, 2-3 million years ago, of us entering into regions of interstellar space that were very cold and dense, that were strong enough to compress the heliosphere down to inside the orbit of the Earth. And so Earth itself, under these conditions, was directly exposed to the interstellar medium instead of being protected by the heliosphere of the Sun. And there's some connection to that with mass extinction events. And so we don't know exactly what's going to happen as we shift from our local plasma cloud to what's known as the G cloud, whether that's happening right now or it's soon to happen within the next 2,000 years or so, and what that process looks like. We also don't know the characteristics of the G cloud, so it could be fairly similar to the local cloud, and therefore there's not expected to be that much energetic change. It could have significantly different plasma characteristics than our local cloud. We do think it's going to be denser though, and that's going to add more of a compressional pressure to the heliosphere. That is what we're going to discuss in today's video. Let's jump right in. Hey everyone, and welcome back to the channel. If you're new here, I'm your space weatherman Stefan Burns, and what we discuss on this channel is what's happening energetically with the Earth by looking at significant geologic events in the geophysical energies that are active, solar activity, planetary resonances, and even cosmic forces. That is what we're discussing today. And so we're going to lay out a little bit of background information so you can better understand what this shift from the local cloud to the G cloud may mean for us here on Earth. And right from the get-go, I want to state that this is a long duration transition that's unfolding. It's not a 1 day or 1 year or probably even a 10-year thing. This is something that's going to occur over probably at least 100 years, if not longer. And it seems that we're going to have that soon within the next 2,000 years or so. But astronomers also think that that shift from the local cloud to the G cloud could be happening right now. So before we get to that, we need to understand some of the energetics of what creates these local clouds and local bubbles and in general the interstellar medium. And to do that, we have to start with our sun and think of other stars as well. So thankfully, our sun emits a whole bunch of light radiation. It keeps the Earth nice and warm. But that light radiation across the entire light spectrum, from radio frequencies all the way up to ionizing frequencies like extreme ultraviolet and X-ray light, it propagates out in all directions. It decays via inverse square law. So every time you double the distance, its strength goes down by 4. But in general, this creates a protective shield around our solar system known as the heliosphere. And this goes out to about 100 astronomical units. We only have 2 probes right now that are outside the heliosphere. That's Voyager 1. Voyager 2, they are on their last legs right now, but they have given us some plasma measurements from outside the heliosphere in this kind of transition zone between the heliosphere and the interstellar medium. And we also have New Horizons, the probe that went by Pluto, that eventually will reach the edge of the heliosphere as well if it survives the next 10, 20, 30 years. So we really don't know that much about the interstellar medium, though we have some other measurements besides just Voyager 1, Voyager 2. But I also want to state that, take some of this information with a grain of salt, because there's probably a lot more that we're going to understand and know about all this in 10, 20, 50 years. So our sun's emitting all this light radiation. Every star is emitting light radiation like this, and stars have different light spectra. Our sun emits most of its light energy in the infrared, visible light, and ultraviolet spectrum, but some are shifted more towards higher frequency light, like extreme ultraviolet and X-ray light. The sun is also emitting a bunch of solar wind out in space, and all of this together creates the heliosphere. And the heliosphere has a magnetic field to it that reroutes cosmic particles away from our solar system. Some of them still get through. We have cosmic particles that rain down to the Earth, but we see this variation in cosmic particle flux here on Earth from solar minimum to maximum. It's greatest during solar minimum when the heliosphere is weaker, and the cosmic ray flux is weakest during solar maximum when the heliosphere is strongest. So our sun is carving out this path through interstellar space, and the sun and all the planets are also moving at a velocity through space, traveling about 220 kilometers per second from this local cloud that we're in to this other plasma cloud known as the G cloud. And the local cloud is the larger zone in interstellar space that has specific plasma properties. And it's influenced not just by our sun, but in fact it's primarily influenced by a few stars that have their light spectrum shifted more towards the higher vibrational wavelengths of light, like extreme ultraviolet X-ray light, which create that zone of higher vibrational plasma because they're able to strip electrons off of neutral hydrogen, just normal hydrogen, which is a positive proton and a negative electron. They have a much greater extreme ultraviolet and X-ray light output to then create greater ionization, therefore more plasma. And as a result, we are in this fairly low density, fairly hot plasma of the local cloud. But there are other zones where other stars are exerting their effects because every star is different and there's clusters of stars, and these are known as Stromgren spheres. So effectively the zone of ionization around a star has a certain size based on the characteristics of that star. And there's also a shell at the edge of the sphere where you have this interaction between the specific plasma characteristics of that Stromgren sphere and the other Stromgren spheres of other stars or clusters of stars. And here we have a graphic showing our local interstellar medium. You see these two axes here. These are both measuring light years. So we have about 50 light years across there and also 50 light years across there. And in general, the local interstellar medium is about 100 light years across in general. So this is not the complete local interstellar medium, but it's a pretty good clear view of it. We see our local cloud right there. We see our sun right there at the edge of it. And here we have our G cloud. There are some other clouds that are also in here, as you'll see. Some are large and some are small. The local cloud is one of the larger ones, but the G cloud is what we have coming up. If I step over, you'll see that we are right on that boundary zone right now. We also see how the other clouds, their vector directions moving this way. So not only is the sun traveling that direction, we also have the clouds also moving to intercept the direction of motion of the sun. Here we have Alpha Centauri. These are the binary stars that are close to us. We also have Proxima Centauri, so it's actually a triple star system. And for example, we see Sirius there. It's in a different part of the local interstellar medium. There's a whole bunch of stars all scattered around, and they all have their own direction of motion. So we are going from the local cloud to the G cloud. And again, we don't know the characteristics of it really that well. It could be quite a change. We've been in this local cloud for a while. And if, for example, the G cloud is very cold and dense, and let's say it's even very dusty as well. Most plasmas are dusty plasmas because they kind of create dust. And so it's much colder and denser. That could really compress the heliosphere because the local cloud right now is fairly high temperature and therefore the density is quite low. So the output of our star, which is, I'd say, middle range, you could say, is strong enough to basically push apart the interstellar plasma and carve our way through without much headache. But if we get a really cold, dusty, dark plasma of the G cloud, this could really compress the heliosphere. And there is some evidence that suggests that that occurred in the past 2 to 3 million years ago and brought the heliosphere actually closer to the sun within the orbit of the Earth. So it was less than 1 astronomical unit to the edge of the heliosphere. Astronomers have been making observations of the cosmos for quite a long time now, and just in the past 50 years or so, we've had huge advancements in our understanding of what exists outside of our solar system by looking at other stars, star-forming regions, nebula, gas clouds, and more. And so some clever astronomers, they calculated where the sun was 2-3 million years ago to the best of their ability, and it looks like the sun was located in the local ribbon of cold clouds in the constellation Lynx. And as the name suggests, this is a cloud of cold, dense plasma. And so then they ran some numerical simulations as to what that interstellar medium would be like in terms of the plasma density and the temperature and how that would affect the solar heliosphere. Here we see some of the outputs of their calculations. So keep in mind, this is a numerical simulation based off of some of the astronomical observations that we have. This maybe did not occur exactly the way that the simulation output, almost certainly that's the case, but there is some geologic evidence for this based off of, for example, iron-60 isotopes. So here we see the heliosphere. Here we have Earth's orbit right there. So the red line is Earth's orbit. We see a little bit better here where we see Earth's orbit like that. The sun is in the center, and we see that heliosphere, because of the local ribbon of cold clouds, was condensed down dramatically, well within the orbit of the Earth. And actually, their calculations brought it down to 0.22 astronomical units. So even Venus was outside of it. And so the Earth would be in the interstellar medium directly before rotating into the heliosphere and then back out at a fairly regular clip. And that in itself would also be a pretty dramatic change to go through every single year. And so it looks like the energetic dynamics as it relates to the plasma that the Earth was interacting with this magnetic field was dramatically different at a variety of times in the geologic past, because we've certainly have moved from local cloud to local cloud to local cloud. We haven't been in one local cloud for the entire existence of the Earth. Astronomers, they've calculated that it takes about 220 million years for our sun to travel around the entire Milky Way galaxy. There is some evidence that suggests that there have been mass extinction events that have occurred when we've gone from the low density zone above the spiral arm of the Milky Way through the higher density spiral arm of the Milky Way, because there's been more impact events, things of that nature. Perhaps it's also through these sort of plasma dynamics with the heliosphere undergoing dramatic changes. How has that also changed solar energy output? That's another big unknown with all of this. But this would have a very strong effect, because now instead of being protected by the heliosphere from those cosmic rays, Earth's magnetic field would be taking all this radiation on directly. And this local ribbon of cold clouds is estimated to have a hydrogen density of like 3,000 per cubic centimeter, so very, very high. Whereas again, our local cloud right now has a very low plasma density. And the G cloud, again, is unknown in its plasma characteristics. We also have the Oort cloud, which surrounds our sun. We don't have any super direct observations of this. All these objects are too dim to be picked out at this moment in time, but we do see these long period comets that come into our solar system. It's theorized that they all originate in the Oort cloud, which is a quite big structure, even up to like 0.1 light years across. Now, the reason I'm bringing this up is, how would the Oort cloud be affected by a sudden change in the interstellar medium, in general, the plasma dynamics? Right now, again, the local cloud has a very low density and a fairly high temperature, but because of that high temperature, that's why they're spread out so much. If all of a sudden we entered into a cold, more dense plasma, and let's say it's especially dusty as well, this perhaps could really perturb a lot of these objects in the Oort cloud, which is basically a massive arsenal of things that you don't want to hit the Earth or other planets. And so this transition from the local cloud to the G cloud could go down with basically no fuss. If it's fairly similar in its properties to the local cloud, it could also be quite a shock. How that would affect the Oort cloud is also a big, big unknown. And while we're on the topic of interstellar space, I'd like to bring to your attention that there are other larger structures that also exist. For example, we have our local bubble. So within our local bubble, there are a whole bunch of these plasma clouds. And so everything is fractal in the universe, as we know. Our heliosphere is a plasma cloud, then there's the local cloud that we're in, and then there's the local bubble, then there's the galaxy, and then there's the galactic clusters, and so on and so forth. But we are also in this local bubble that is created by more significant light output from some really big stars and star clusters. For example, the Pleiades, they are very highly vibrational, and the light output that they emit, these are very big stars, they influence their interstellar medium in space. And so this local bubble is something that we're not exiting anytime soon to the best of our knowledge, but there are structures within it outside of just these clouds created from supernova explosions and more that we do transit across at times. And so on a geologic sense, this affects us. But as it relates to what's happening right now, this is just something to know, not necessarily something that's going to be directly affecting us as significantly as the movement from the local cloud to the G cloud. And again, that's also something that is likely going to play out over a long time. We may still be in the local cloud. We may already be in that transition zone from the local cloud to the G cloud, but astronomers think that that movement into the G cloud is going to occur in less than 1800 years. Right now, we are in a solar maximum period. This is a peak in a 12-year cycle of solar activity. We are also in a grand solar maximum, which is a longer duration peak in solar activity. This started after the last grand solar minimum, which was the Maunder minimum in the 1600s. Now we've had 300 years of really strong solar activity. Solar cycle 25 is continuing that trend. Eventually, we'll have a new grand solar minimum. We don't know when that will be. We also have these historic planetary resonances that are occurring this year and next year with the great conjunction between Saturn and Neptune. So there's a lot that's already on our plate at this moment in time. And underneath all that is this historic, gigantic shift in our interstellar energy, going from the specific plasma characteristics of the local cloud to the new and unknown plasma characteristics of the G cloud. And because this is our interstellar medium, it's really the background energy that everything else is resting upon. We don't know how changing plasma dynamics of these clouds affects the Earth or the sun directly. Again, we have that evidence from maybe 2-3 million years ago, some geologic evidence, but in general, it's a very, very big unknown. And so this could mean that there's increased cosmic rays coming in. This could mean that, for example, if you go to an even lower density cloud, that the heliosphere expands outwards even more. How that changes the energetics of the sun, the solar wind, that's a big question, a big unknown. There are some theories out there that the sun, in fact, is driven by these electric currents that run through interstellar space called Birkeland currents. They're superconducting highways of energy, and they feed down into the poles of the sun and drive the sun. This is an interesting idea. And those would run through interstellar space. And so how does a new interstellar environment affect these Birkeland currents, for example? Again, they are kind of a theoretical thing. We don't know if they exist 100%, but there's some good evidence for that. These are all big unknowns. How the heliosphere would change, how that affects our planet, and what that does to our magnetic field. Is it under more stress now, less stress? And perhaps if there's a big change in the interstellar medium and it does get colder and denser, and our magnetic field is under greater pressure now from these interstellar forces, perhaps the Earth responds by strengthening the magnetic field, or perhaps it's not able to maintain the strength, so the magnetic field collapses. Same with the sun. All these dynamics at play. There's so many unknowns with this. So I recommend, if you're interested in this, to just simply meditate on this and to not get worked up or worried about it, because we don't know what we don't know. And if you have faith in everything being all right, then there's nothing to worry about. But it's an interesting thing to meditate on, especially as it relates to how the background energies that we exist within perhaps guide the evolution of consciousness in our solar system, and specifically here with us on Earth. So if you enjoyed the video, please smash that like button. I've been your host, Stefan Burns. And in general, if you'd like to stay up to date with what is happening with the Earth energetically, also the sun and solar system and beyond, then you can subscribe to the channel. I release videos almost daily. Thank you all so much for watching. I am wishing you all well. I'll keep you up to date on this as I learn more information. I'll create new videos, and I'll see you all in the next one.